Hi, welcome back. This is a summary of notes 6.1.1, and I'm Miss McClellan here to go over it with you. So, the goal for note 6.1.1, the goals were twofold. First, you would be able to investigate two types of special right triangles to find the patterns in their structure. And second, when given one side length, you can find the other two side lengths for 4590 and 306090 triangles. So in this chapter, we learn about several special right triangles, being able to recognize them as families of similar triangles will help us to enable us to determine the lengths of the sides and will save us time and effort. The first family of triangles is called 30, 60, 90 triangles. Should be S here. And they look like this. And it's a special right triangle with acute angle measures. This is the definition. A special right triangle with acute angle measures of 30 degrees and 60 degrees. These side lengths are always in the ratio of 1 to √3 to 2. And we figured that out using the fact that an equilateral triangle has angles of all 60 degrees. And if you cut that equilateral triangle in half, you get a 30, 60, 90. And if the hypotenuse is length 2, then the smaller leg is length 1. And using the Pythagorean theorem, we found that the height would be from 1 squared plus the height squared equals 2 squared, and that this had to be 3 squared. Sorry, the square root of 3 squared, because I need this number to be 3. So 1 plus 3 is 4. So this is height √3, which is summarized right here. I'll just color in the part of this we were talking about. Okay, and then there's a 45, 45, 90 triangle. That's the special right triangle. With acute angle measures of 45 degrees. And the side lengths are always in the ratio 1 to 1 to the square root of 2, which we see right here. This would be a squared plus a squared equals 2a squared. Using the Pythagorean theorem, which is leg squared plus y squared equals hypotenuse squared, often displayed as a squared plus b squared is c squared, where c is the hypotenuse. We've got some examples. So an example using 45, 45, 90, a ratio to solve a Pythagorean theorem problem. So if I have a triangle, and I'll draw one right here for us, which is a right triangle isosceles, such that the acute angles are each 45 degrees, how do we find x? Well, there are two ways. We can use the Pythagorean theorem, 2 squared plus 2 squared equals x squared, which gets us 4 plus 4 equals x squared, which is 8 equals x squared, which is 2 times the square root of 2 equals x squared. Equals x. It might not be obvious that when I take the square root of both sides, the square root of 8 is 2 √2, but it is. because the square root of 8 equals the square root of 4 times 2, which is 2 times the square root of 2. Another example, 45, 45, 90 using properties of special right triangles. So we just solved this with the Pythagorean theorem, but the special right triangles might be faster. So let's look. Same triangle, 2, 2, 45, 45, and x. Now from our notes, we have the leg equals a. That's from up here. That's where 2 was. So we're drawing connections between this drawing and what we're doing in this problem. The hypotenuse should be equal to a times the square root of 2. And a in this case is 2. So what I end up with is the hypotenuse, which is x, 2 times the square root of 2. And it's correct. They're both right. So x is 2 root 2. Okay, another example. 30, 60, 90 using the Pythagorean theorem. Okay, I've got a 30, 60, 90 triangle with lengths 4, 8, and x. Using the Pythagorean theorem, I do leg squared plus leg squared equals hypotenuse squared. So 4 squared plus x squared equals 8 squared. That's 16 plus x squared equals 64. I subtract 16 from both sides, and I get that x squared is 98. I take the square root of both sides. I have x is the square root of 98. You might think that we're done, and we could be, but there is a more common way to write this number. 98 is equal to 2 times 2 times 2 times 2 times 3. If you were to break this into its prime factorization. So this becomes the square root of all of these things. Each pair can come out. So this becomes 4 root 3, which is equal to x. I'll leave this as x equals the square root of 98 because I feel like that's more natural when doing the Pythagorean theorem. But I want to show you that these two numbers are the same because next when we solve it using the special right triangle formulas, you're going to get 4 root 3. Okay, so same triangle. This is a 30, 60, 90 triangle, hypotenuse 8, long leg x, short leg 4. So from our notes, we have the hypotenuse. And equals 2a. That's from up here. The longest side is 2a. And that for us equals 8. And we have the short leg equals 4, which would just be a. And we have the long leg equals x. So from our notes, we know that the long leg is going to be root 3 times a. Well, I know what a is from the short leg. So my final answer is that x equals root 3 times 4. And we usually write the number in front of the radical so that we don't end up accidentally writing it inside the radical. So the final answer would be x equals 4 root 3. And they're the same. Okay, that concludes our notes summary. I hope you have a great day, and I'll see you next time. Bye. Gotta close this.